Picture the entire universe, all of it, every star, every planet, every speck of light scattered across the infinite dark. Now ask yourself a question that seems simple, but is not. Is the universe growing larger? Is it shrinking? Or does it simply sit there frozen in time, unchanging forever? For most of human history, no one thought to ask. The heavens seemed permanent, fixed, eternal. But when we finally looked closely at the equations that describe gravity, spacetime, and the fabric of reality itself, something deeply strange appeared. The universe, according to the mathematics, cannot stand still. It must either expand or collapse. There is no middle ground, no rest, no balance. And yet, when we look up at the night sky, everything seems calm, stable, unmoving. So we are left with a choice. Either the universe truly is collapsing or expanding, and we simply have not noticed yet, or there is something else, something hidden in the equations, a force we have not yet seen, a term we have not yet understood. This is where lambda enters the story, the cosmological constant, a single symbol that changes everything. Let us begin with what we know to be true. Gravity pulls. This is not controversial. Every object with mass attracts every other object with mass. The Earth pulls on the Moon. The Sun pulls on the Earth. Galaxies pull on other galaxies. Gravity is always attractive. It always draws things together. This is the foundation of general relativity, and it has been tested countless times. It works. It is correct. But here is the problem. If gravity only pulls, then the universe cannot remain still. Imagine a massive web of stars and galaxies, all pulling on one another. What happens? They move closer, they collapse inward. The entire universe should be shrinking, falling in on itself, drawn together by the relentless pull of gravity. And yet, when we observe the universe, it does not appear to be collapsing. The stars remain in their positions. The galaxies do not seem to be rushing toward one another. Everything looks stable, quiet, at rest. So we are forced to ask, why does the universe not collapse? There are only a few possibilities. Perhaps the universe is so large and gravity so weak at vast distances that the collapse simply takes an impossibly long time. Perhaps we are living in a brief moment of balance, and the collapse will begin later, or perhaps something is wrong with our understanding. Or perhaps there is a force we have not accounted for, a force that pushes outward, a force that opposes gravity, not because it is anti-gravity, but because it is woven into the structure of space-time itself. This is lambda, the cosmological constant, a term that can be added to the equations of general relativity, a term that represents a kind of tension in the fabric of space, a pressure, a repulsion that does not come from any object or field, but from empty space itself. Let us think carefully about what this means. In general relativity, space-time is not a passive stage where events happen. Space-time is dynamic. It curves, it bends, it responds to the presence of mass and energy. When mass is present, space-time curves inward, and we call this gravity. But what if space-time itself, even when it is completely empty, has a kind of energy, a baseline tension, a pressure that pushes outward, resisting the inward pull of gravity? This is not a new substance. It is not a particle. It is not a field in the traditional sense. It is a property of space itself. Empty space, it turns out, might not be truly empty. It might have a kind of springiness, a resistance to being compressed, and this resistance, if it exists, would create an outward push, a cosmological repulsion. Now, let us return to the problem of the static universe. If gravity pulls everything inward and lambda pushes everything outward, then perhaps the two forces can balance. Perhaps the universe can remain still, neither expanding nor collapsing, held in perfect equilibrium by the opposition of these two forces. This is the reason lambda was introduced, not because we observed it directly, not because experiments demanded it, but because the mathematics of general relativity, when applied to the universe as a whole, predicted motion, and motion seemed wrong. The universe appeared static, so a term was added to restore balance. A constant was introduced to make the equations match what we thought we saw. But notice what has happened here. We have not explained lambda. We have not derived it from deeper principles. We have simply placed it into the equations because it solves a problem. It is a patch, a correction, a way to make the theory agree with observation, and this is troubling, because in physics we do not simply add terms to our equations whenever we find something inconvenient. Every term must have a reason, every force must have a source, every constant must have a meaning. So what is lambda really? What does it represent? One possibility is that it represents the energy of empty space. In quantum mechanics, we learn that the vacuum is not truly empty. Even in a region of space with no particles, no light, no matter at all, there are still fluctuations. Virtual particles appear and disappear, fields tremble with quantum uncertainty. The vacuum has energy. And if the vacuum has energy, then according to general relativity, it must also have gravity, but not ordinary gravity. Vacuum energy would create a kind of negative pressure, a tension, an outward push. This is a profound idea. It suggests that lambda is not arbitrary. It is not a patch. It is a real physical effect arising from the quantum nature of fields and particles. It is the gravitational effect of the vacuum itself. But there is a problem. When we calculate the energy of the vacuum using quantum mechanics, the numbers are enormous, catastrophically large. If the vacuum truly had that much energy, the cosmological constant would be so strong that the universe would tear itself apart in an instant. Atoms would not form, stars would not exist, life would be impossible. And yet here we are. So either the calculation is wrong or something cancels out the vacuum. Energy almost perfectly, leaving behind only a tiny residue, but we do not know what that something is. This is one of the deepest mysteries in all of physics. Why is lambda so small? Why is it not zero? Why is it not enormous? Let us step back and think about the role of lambda in the equations. In general relativity, the curvature of spacetime is determined by the distribution of mass and energy. The more mass, the more curvature. The more curvature, the stronger the gravity. This is the essence of the theory. But when we include lambda, we are saying that spacetime has a kind of intrinsic curvature, a baseline bending that exists even in the absence of matter. This is strange. It means that empty space is not flat. It means that geometry itself has a tendency, a preference, a direction, and this raises a question. If spacetime can curve on its own without any matter present, then what determines the amount of curvature? Why does lambda have the value it has? Why is it not larger or smaller? We do not know. Lambda is a constant, but it is not explained. It is a number we must measure, not a number we can predict, and this is unsatisfying. In physics, we seek understanding. We want to know not only what happens, but why it happens. Lambda tells us what the universe does, but it does not tell us why. Now let us consider what happens if lambda is not exactly zero. If lambda is positive, space pushes outward. If lambda is negative, space pulls inward, adding to the effect of ordinary gravity. And if lambda is precisely zero, then space has no intrinsic curvature at all. Geometry is determined entirely by matter for many years. It was assumed that lambda must be zero, not because this was proven, but because it seemed the simplest choice. Why should empty space have any curvature at all? Why should geometry have a preference? Zero seemed natural, clean, elegant, but nature does not always choose elegance. Nature chooses truth, and the truth, as it turns out, is more complicated. When astronomers began to measure the motion of distant galaxies, they discovered something unexpected. The universe is not static, it is not balanced, it is expanding, and not only expanding, but accelerating. Galaxies are moving apart faster and faster, as if something is pushing them. This observation changes everything. If the universe is accelerating, then gravity alone cannot explain what we see. Gravity pulls, it slows expansion. It does not speed it up, so something else must be present, something that pushes, something that drives galaxies apart, and the simplest explanation, though not the only one, is lambda. A positive cosmological constant would create exactly this effect. It would push space apart, causing the universe to expand faster and faster over time, but let us be clear about what this means. It does not mean that galaxies are flying through space. It means that space itself is growing. The distance between galaxies increases not because they are moving, but because new space is appearing between them. This is the expansion of the universe, and if lambda is positive, this expansion accelerates. Now think carefully about the implications. If lambda is positive, then the universe has a kind of built-in tendency to grow. Space wants to expand, and as the universe grows larger, the effect of lambda becomes stronger because lambda acts on every point in space. The more space there is, the more lambda pushes. This leads to a strange conclusion. If lambda is positive, the universe will expand forever. Galaxies will move farther and farther apart. Stars will burn out. The universe will grow cold, dark, and empty. Everything will drift away from everything else until nothing remains but isolated specks of matter separated by unimaginable distances. This is not a comforting picture, but it is the picture that emerges from the equations. If lambda is real and positive, of course we must always be. Careful observations can be misinterpreted, models can be wrong. What we think is lambda might be something else entirely. Perhaps there is a new field, a new force, something we have not yet discovered. Perhaps the equations of general relativity need to be modified when applied to the universe as a whole. These are open questions. They are being studied. They are not yet answered. But here is what we can say with confidence. The universe is not static. It is changing. It is expanding. And something is driving that expansion. Whether that something is lambda, or a new form of energy, or a modification to gravity itself, we do not yet know, but we know it is there. We can measure its effects. We can see it in the motion of galaxies, in the light from distant stars, in the structure of spacetime itself, and this brings us back to lambda, the cosmological constant, a term that was once introduced to keep the universe still, a term that seemed unnecessary when the universe was discovered to be expanding, a term that was set aside, forgotten, dismissed as a mistake, and yet decades later lambda returned, not because anyone wanted it, not because it was philosophically appealing, but because the data demanded it. The universe is accelerating. And lambda, or something very much like it, is the simplest explanation. This is how science works. We do not decide in advance what the universe should be. We observe, we measure, we calculate, and we follow the evidence wherever it leads, even if it leads us to ideas that seem strange, even if it leads us to forces we do not fully understand, even if it leads us to questions we cannot yet answer. Lambda is one of those questions. It is a constant that appears in our equations. It is a number we can measure, but we do not yet know where it comes from. We do not know why it has the value it has. We do not know if it is truly constant or if it changes over time. We do not know if it is fundamental or if it is a placeholder for something deeper. But we know it is important. We know it shapes the universe. We know it determines the fate of everything we see, and so we continue to study it, we continue to measure it, we continue to think about what it means, because understanding the universe is not about having all the answers. It is about asking the right questions. It is about being honest about what we know and what we do not know. It is about following the trail of evidence, step by step, even when the path is unclear. Lambda reminds us that the universe is full of surprises, that reality does not always behave the way we expect, that empty space is not truly empty, that geometry is not passive, that the fabric of space-time itself has structure, energy, and behavior, and perhaps most importantly, Lambda reminds us that our understanding is always incomplete, that every answer leads to new questions, that the universe is vast, strange, and endlessly fascinating. We live in a universe where space itself can push, where emptiness has energy, where the very geometry of reality has a will of its own. This is not the universe of common sense. It is not the universe of everyday experience, but it is the universe we inhabit, and the more we learn about it, the more astonishing it becomes. So when we look up at the night sky, we are not just looking at stars, we are looking at the consequence of forces we barely understand. We are looking at the result of a balance between gravity and lambda, between inward pull and outward push, between collapse and expansion. And we are reminded that the universe does not owe us simplicity. It does not owe us comfort. It only offers us truth, and truth, when we are brave enough to face it, is more beautiful and more strange than anything we could have imagined. This is the lesson of Lambda. This is the gift of the cosmological constant, not an answer, but a doorway, not a solution, but an invitation to keep looking, to keep wondering, to keep searching for the deeper principles that govern reality, because the universe is not finished revealing itself, and neither are we finished learning.